Okay, if you can hear me, let's get started recording for the 9 o'clock lecture. Okay, so two things on defects, or what's the effect of sort of messing up the case-based data on the image. So we'll talk about these are like standard things you would talk about in sort of an engineering MRI class. So the Fourier phase shift theorem, it's usually just called the Fourier shift theorem, but it's really the Fourier phase shift theorem. And then very closely related, the Fourier frequency shift theorem. And so this, we kind of already talked about this phase shift when we talked about the original descriptions of K-space. Like if you mess with the Fourier phase, what does that do? It causes a shift in the image. This other one, Fourier frequency shift theorem, is a little more counterintuitive. But we'll go over those first, and then graduate up to what is the effect of a local B0 defect. So it turns out it has to do with the second one, and it's something that's caused by the fact that the data was collected over time. So it's an interaction with between a B0 defect and the fact that you're collecting the data over time. So that's the plan. So we'll start off with the Fourier shift theorem, but it's the Fourier phase shift theorem. And this is a very simple thing, which, like I said, we've kind of already gone over in multiple times, but it never hurts to go over things about like 6 times in a row, at least if you're like me, because the mind is recalcitrant, and it attempts to sort of, it's hard to change the way it thinks, which is a good thing, because you don't want your mind to sort of be like Jell-O, and somebody says something and boom, it changes your mind. You got to sort of strike back. That's why it's hard to sort of learn new things. Okay, so here's the Fourier shift theorem. And so if we write out our inverse Fourier transform, so this is inverse Fourier transform because we're taking case-based data on the right and we're generating an image out of it. So this is the inverse Fourier transform. So what the Fourier shift theorem says is a constant spatial offset. So this guy's a constant. I'll just write it out for 1D Fourier transform, but you can expand to 2D easily. So that's a constant spatial shift. And then this guy's the variable. So that's the variable that extends across the image, the image brightness, basically, at each xy point. And so the Fourier shift theorem says that a spatial shift in the image is caused by a phase shift. And so here's our inverse Fourier transform. So we're summing across all of K-space, all spatial frequencies. And so here's that phase shift. So minus I 2 pi k kx multiplied by x0. So remember this guy's a constant, not a variable. So that's a constant. So that's our phase shift. And we're multiplying that by our regular inverse Fourier transform. So here's the k-space complex valued k-space signal at spatial frequency, which we're summing across. And then we have our normal inverse Fourier transform, which is the same as the forward Fourier transform, except that we multiply by e to the plus I, 2 pi k x x, and that x is a variable. So this guy is a variable, and then we're summing. We're summing across for every spatial frequency. Okay, so that's our Fourier shift theorem. And so what is it in words? So we just put it here. So Fourier, shift phase shift theorem. So the Fourier shift theorem is basically phase shift in spatial frequency. That would be this guy. Phase shift in spatial frequency domain causes image shift. So that's in words. So I mean, it's really sort of a trivial thing if you look at it. So what we're doing here is we're just multiplying by this complex number. Remember, this is a complex number of amplitude 1, which has this angle, and that's an angle, and so we're just adding that angle onto this angle because this thing is another angle over here. That guy right there is another angle, and we could essentially just incorporate that thing, this angle, into this angle, because when we multiply two exponentials, that's equivalent to adding their exponents. And so if we just added this thing into this exponent, what are we going to get? We're basically just going to get, so if we just sort of combine these two, we'll get, and we'll essentially get, e to the I 2 pi kx, and then just combine them. So just x minus x0. So basically we just combine those two. We've stuck the negative there moved it into the x. That's where the negative came from. So you can see right here, there's the spatial offset. So it's kind of like just a trivial outcome, because you just have, our spatial frequency k-space data multiplied by our normal inverse Fourier transform term, except we've got a spatial shift here, and that just turns into this spatial shift here. So when you write it out this way with a separate term for the phase shift, then you can sort of like focus on the, what is this doing to the k-space data? It's actually, what is that minus x doing to the k-space data? It's basically just messing with the phase of the k-space data of every frequency. So that's an important point here, is that it's modifying every frequency. So angle, so this guy, modify, every freak. Okay, so what is this just visually, spatially? So if we just draw one frequency, so this is image, this is not k-space, so image domain. And we've got, so let's draw a brain in there. So here's brain in there. And so say we're doing, spatial frequency 2. well, we have attempted to stamp on sort of two spin phase stripes like this. So that's our, if we plot the spin phase, it looks something like this. So this is like 0 and 2 pi. So the idea is we attempted to stamp on two cycles of spin phase. And so this is for example, kx equals 2. Okay, so two cycles of spin phase. And now we're going to modify that by multiplying every spatial frequency by this complex exponential, which is just adding an angle to it. So we're just going to add an angle to the spin phase at each point. And so here's our, add phase error angle, okay? So we add a phase error angle, and what does that do to our spin stripes? So what it does is it will, if we draw out the graph first, say we were supposed to be at 0 at the left side, but if there was a phase error, say it moved us up, wrapped us all the way around a little bit, and so you end up with something that looks like this. And then it doesn't get quite up to the, back up to 2 pi. So all it did was, you can see what it did is it just basically took this spin phase stripe pattern and just shifted it. And so now the wraps are going to occur here. So here will be the lowest phase, and then so it will have just shifted these stripes over, just physically shifted them over. And so when you look at it that way, well, it's pretty straightforward that it's going to cause a spatial shift in our image. So the important point about this is, so this is not a gradient, okay? I call it like a pedestal of spin phase, because we're adding phase to everybody, but equivalent amount of phase to everybody across the whole image. And so that's an important thing. So don't get confused and think of this as a gradient. It's not a gradient. We just sort of like added a pedestal of phase to everybody. And it also added it to every frequency. And so that's a little sort of slightly weird, because that means higher frequencies, say like 20 stripes. Let's just draw one of those out. So say we had, well, not do 20. How about like, how about however many I end up with? So say we put on this many stripes, like that. So what is it going to do to those? It's not going to move them as much, right? So it's just going to move them in proportion to the size of the stripe. So this guy is only going to be moved something like, if we move this one, say about a quarter of a stripe. So this was, this was like about 90-degree phase, plus 90-degree phase. So we're only going to move this guy, a small amount. All right, that guy's just going to be a little bit off like that. So this is, how many? 1, 2, 3, 4, 5, 6, 7, 8, 9. So this was, kx equals 9. This guy was, kx equals 2. So the higher frequencies, they're not going to be moved as much, but it all works out in the end. And if you work it through, what will happen is it will completely shift the image without blurring it at all, just shift it in space. So that's the Fourier phase shift theorem. And like I said, we remember back in the day we talked about like a cosine brane. Remember, and we said if we change the phase of the case-based data. Like if we went from, the phase was supposed to be like 0, but we messed with it in this special sort of Hermitian way, then what did that do? That actually just shifted our image when we on Fourier transform. The same thing. So that's the Fourier phase shift theorem, which is you add some phase onto the case-based data. So this guy is, case-based data. So anything that adds phase onto the case-based data or subtracts it is going to essentially just get turned into a spatial shift. So the gradients could be nonlinear. That will cause a spatial shift in the image. Or you estimated the center frequency wrong. That will cause a spatial shift in the image because it's going to affect the phase of all the spins. Okay, so is this one clear? So that's Fourier phase shift theorem. So alternatively, we could mess with the frequency. And so this one's stranger. This one's kind of a little strange because like phase, usually think about phase and then how does that get turned into like a completely rigid translation of the image. But the Fourier frequency shift theorem is what if we somehow messed up the frequency here, the frequency of our case-based data. So what does that turn into? And so it turns out that turns into a phase shift in the image. So here's the phase shift in the image. I 2 pi. And then we've got subscript and the subscript. So this is kx and then a subscript on the subscript, kx0. So that's a constant frequency shift. So this is kind of like this constant. So this is a constant frequency, shift. So that thing is a constant. This whole term is a constant, and it's going to essentially shift the phase of the image. Now remember, the phase of the image is supposed to be 0 because we're supposed to have a real brain, and so it shouldn't have any imaginary part. But now we're going to create an imaginary part in our image. And so if we write out our inverse Fourier transform, it's the same equation there. So here's our case-based data, complex case-based data, but now it's going to have a frequency shift in it. So here's that subscript on a subscript. So this guy is, constant frequency shift. And we'll say like how you could possibly get that. And this guy's a variable. That's the variable that we're integrating over. And then it's just a regular inverse Fourier transform. So it's e to the I 2 pi kx, that's a variable, times x. And summed across all spatial frequencies. So this guy is the Fourier frequency shift theorem. And so in words, again, what is it? It's a frequency shift in spatial frequency domain, spatial frequency domain causes phase shift in image. And what is that? That's kind of, this is a little weirder. So what's going on here? So, and how could this occur? So this one we said, how could this one occur? The phase shift in spatial frequency domain. How could that one occur? That could occur like maybe we misestimated the center frequency. So that one, or maybe our shim was off, or maybe there was a gradient nonlinearity, or maybe there was a B0 problem somewhere in the image. So many things could have essentially messed up the phase of our case-based data. But now we're talking about something else. We're talking about what if we somehow got the frequency of our case-based data wrong. And so how could we possibly do that? Well, a simple example would be, what if we, normally we try to make the echo happen right in the middle of case-space like this, so that the echo is like, if I drew one of the echoes out, it looks like that, so that we go through, we have timed the echo so that when we collect all our data points in case-space, so here we're collecting all our data points, when we get to the center, that's actually the center of the echo. So that's the way we want to do it. But say we did something else. Say we somehow screwed up, but the timing was incorrect of our data point collection. So say we just accidentally got behind and we didn't start collecting data until too late, and the echo ended up over here. So this is when actually when all the spins came back into phase, the center of k-space. But say we didn't call it the center of k-space. We just got screwed up, or there was some timing in the gradients or something like that. And so the echo occurred like, halfway through. And so we wanted that to occur at spatial frequency 0, but instead the echo occurred at spatial frequency 30 or something like that. And so what would we call that? We would call that like an echo centering error. Now, that seems like, that's like a major infraction. Like the echo was supposed to be in the middle and you put it like, way out here. Wouldn't that screw things up? And the surprising answer is that you would not see the effect of this in the amplitude image, according to this theorem here. Because what this theorem says is, if we have an offset in our frequency in k-space, again, this is like our phase, or our frequency error, frequency shift. So we thought it was, spatial frequency 0, but in reality it was spatial frequency minus 30. That's what this offset here, this constant offset means. What is it going to do? It's going to basically just not mess up our image at all, except it's going to change the phase of the image. And so what does that look like? So if we take this data, this shifted data, and inverse Fourier transform it, we're going to get a complex number. So, at each point, each single data point is going to look something like a complex number like that, and then it will have a real part and an imaginary part, and there's the phase angle, and there's the amplitude. When we actually look at that image, what's going to happen? Well, after we, inverse FFT it, we look at the image, and the image is just fine, no problem. It just looks like a brain image. So that's the amplitude image. And so it's not going to mess with that at all. It's going to be the same values, but the phase of it is going to be wrong. And so what does that mean? Well, normally we throw that out. So when this is what appears on the console. This is the console image. You just see the amplitude image. And the amplitude image wasn't changed. All you did was you just messed with the phase angle. And so what does the phase angle look like? Well, what is the phase angle supposed to be? It's supposed to be about 0. So if you look at if you just make an image out of the phase, so what should it be? It should be like a sort of a brain shape with all 0 in it. And then there'll be just noise out here because there'll be sort of random phases out here because the signal is so tiny. So you'll see just a bunch of speckle out here of random phases, This is kind of random phase in noise, in error, because those signals are tiny. And then this should all be basically 0. But what will it actually look like if we were off by, say we were off by 4, so that I can draw it. So what will happen is there'll be 4 stripes of image phase. And so what you'll see is, there'll be like a 0 image phase there, and then it will go up, and then it'll go up and more, and then there'll be like a 0 image phase here, and then so there'll be these little jagged stripes in image phase in the image. And if you look at the cover of Buxton's book, he's got a picture of one of these on there. You can see what it looks like. So this is the actual phase, the image phase. So remember, this guy here is all image. So this is k-space on this side, and then we're doing an inverse Fourier transform, and this is image. So and this is the image up here. Yeah. So surprisingly, it doesn't do anything. It just screws up the image phase. And when you're first thinking about echoes, so if you looked at k-space that was shifted like this, you'd have a giant bright spot, which is the real 0 spatial frequency, and it was not in the center of k-space. No problem. So that's sort of strange Fourier land. So these are, you can see they're closely related to each other. This one is a shift in phase that we messed up the spatial frequency by shifting the phase. That's actually damaging. That causes a big spatial movement in the image here. That's a big effect. It could move the image halfway across the field of view. This one, by contrast, we somehow screwed up where we thought spatial frequency 0 was. Hardly does anything. It just adds some image phase over here, but the image phase typically we're throwing out. You don't even see that phase angle. Okay, so how's it going for the Fourier shift theorem, Fourier phase shift theorem, and Fourier frequency shift theorem? It's sort of clear. We've just kind of gone over it from all different angles. This is just the way that it's normally written out. Sort of written out. Is that okay? Questions about that? So a phase shift causes a spatial shift. A frequency shift just causes a phase shift in the image, which is kind of less familiar because the image phase should be 0 if everything was correct, because it's a real image. Yeah?
What will we use from like a practical, what will we use the phase shift image for?
Oh, the phase, yeah, so you can use this, so what would you use this phase shift image for? A typical thing you would use this for is you could use it to try to estimate what the B0 defect was. That's an example of how you might want to use a phase shift image. So there's several things you could do with that. Normally we just throw it out because you just mainly want to see the amplitude image of the brain. But you can use you can tell the scanner to save it, and then you could actually use that to estimate what the B0 defect is, especially if you have two echoes, because you can sort of, if you have a second echo after there's been more time for the phase shift to occur, you can sort of, you need two echoes in order to estimate that phase shift. So you would collect two phase images with two different echo times and then try to figure out the B0 defect. So you can use this information is helpful because it's indicating essentially where the phase shift, where the B0 defect is messing with the phase. But if you're just looking at the amplitude image, then you wouldn't see it. Yeah, I mean, the part that's kind of counterintuitive is you think of an image like an image just has one number at each point. But when we do the inverse Fourier transform, you're getting this image you're getting back is complex. It should be complex with the imaginary part equals 0, but it never is. And it really never is in this case. And in fact, it's possible you can do something, there's a pulse sequence called asymmetric spin echo. Asymmetric spin echo. So what you could do is you could collect an image and get a gradient echo in the middle of the image, and then set the timing of your 180 pulse to get a spin echo over here. So you could get like a spin echo over here and a gradient echo over here that's not lined up with it. And when you look at that, you say like, wow, that's just wrong. How could you get sort of an image out of that? But because of this second theorem, that it's going to cause some phase error problems. But this will work fine, like with an offset, a spin echo that's actually offset from the center of K-space. There's several reasons why you might want to do this if you want to. Last time we talked about how you might do spin echo to slightly weight your image toward smaller capillaries. This is one way of doing that. You could sort of do a gradient echo EPI and then arrange the spin echo to come a little bit off center so that you get sort of, you don't completely kill your signal, but because you got some gradient echo signal left there, but you maybe weight your signal a little bit more toward smaller blood vessels. If you just look at this, it just seems wrong. Like, how could I sort of make the gradient echo occur over here and the spin echo occur over here? It seems like it would mess things up, but it doesn't. It just messes up the image phase. Okay, so that was Fourier Fourier phase shift theorem and Fourier frequency shift theorem. Now let's just talk about what you actually deal with every day if you're doing any kind of functional MRI, which is distortions caused by B0 defects. And so how does this work? So at first you would think, and I did too, that it must be like the Fourier shift theorem. Because if you mess with the phase, it's going to cause a spatial shift in the image. Sort of natural enough. And but it turns out it's not. It's not what it is. So it's really an example of the Fourier frequency shift theorem. This strange one that I'm erasing right now. So how does that work? So I'll first go over like how you might think it would work. And then we'll go over how it actually works. So how you might think it would work. So what are we talking about? We're talking about B0 problems. And where do those typically occur? If here's the brain, I mentioned this in the ADM lecture, you got your ear canal, which goes right underneath the brain. There's air. Ear canal is quite long, and there's this air that goes right under the brain. And when you have air right next to magnetizable stuff, your brain is magnetizable, the air isn't, that can cause a little local disturbance in the B0 field. And so what happens is, all around this little region there'll be some distortion. And another possible problem is the air in your olfactory system. So there's something called the olfactory bulb. That's where your olfactory epithelium attaches to. And there's a very thin little plate of bone called the cribriform plate right here. It's got some holes in it. So, normally the bone is nice and thick, but it thins down right there in order to allow the olfactory bulb to get connections from the olfactory epithelium. So this is right where the olfactory epithelium is. It's got to send axons through into the olfactory bulb. And so you've got some air that's right next to the brain. And so what's going to happen is there'll be kind of a big defect right in this region of the brain. So there's some air, like I mentioned last time, there's some air in the sinuses in the back of your skull, and that can cause like a B0 problem there. Several different places for these things. So these are B0 defect. And that's going to cause the image to get messed up. And I, last year during all the COVID madness, your eye is right about here. Right here's your eye, and then your nose sort of coming down here. And some, back in the day when they were forcing people to get all these nasopharyngeal samples, what would they do? Here's your nostril. They're supposed to be aiming for the top of your throat. I apologize if anybody ended up having to get one of these throat. And so what they were trying to do, what they were supposed to be trained to do, was here's your ear here. They're supposed to stick the swab in and swab the back of your throat. But I've seen pictures on the internet of somebody sticking the swab in like this. And there were cases of somebody who actually severed the olfactory nerve and punctured the cribriform plate, causing the cerebrospinal fluid to come out. So if you ever get one of these, tell them, aim toward the ear. Do not go up. Do not stick that swab up. This is where the throat is. It's not up there. So that's the air. So now you'll remember it. That's the air right there that causes the B0 defect. That's a really big one, big B0 defect. And so how did I think it worked? So here's what I wrote my notes up years ago in the wrong way. And then I finally tried to do some MATLAB, and I said, I guess that wasn't the right answer. So let's sort of imagine we've got a brain in here, and let's say that we turn ky up to 4. So here's ky up to 4. So we put 4 stripes on the brain. So like here's the bottom, say here's the bottom of the stripe, and then it's going up. And so if you look at the phase, we're slowly going like this. So we're trying to do that. 4 stripes on the brain. Now imagine you have a B0 defect, plus. So this is our our original no defect, and here's our local B0 defect. And so say there's like a local B0 defect somewhere in this range. And so what does that look like? That looks like no defect here, and then maybe the magnetic field is just overly big right there. So a little defect like that. A little increase in the magnetic field. So what is that going to do? Well, it's going to mess up the stripes, right? So what does that do? So this is, original no defect. Here's local defect, and this is our data point with defect. So it's going to mess up the phase of the stripes. And so what is that going to do? If it was a positive one, it's going to squish the stripe. So if you look at this here, what's going to happen? Well, there's going to be this stripe. We were attempting to put it on, across the brain like that. So we were attempting to put on a stripe like that. But when we got to the point where the defect was, there's going to be extra B0. So this is, plus B0. And so what that's going to do is it's going to bend the stripe down like that, because the phase will be advanced there, and so we'll get to 360 more quickly. And then these stripes will be okay. So there's no question it's going to bend the stripe. It will bend all the stripes. So it will bend the higher spatial frequency stripes. They won't move as much because they're higher spatial frequency, but it's going to distort all the stripes. And then, so this is the garden path. This isn't the actual explanation. I'm going to just put it here just so you can make sure that you don't think it works this way like I did. So now we recon with undistorted stripes. That's ft minus 1. So we reconstruct with undistorted stripes, and what would this do? Well, it seems like it should distorted stripes. That's ft minus 1. It seems like it should cause a shift, right? So what what does it do? Well, in fact, this is an example of the Fourier frequency shift theorem. Because what have we done? We've shifted the spatial frequency here. That's a higher spatial frequency than it should have been. So in fact, there's an example of Fourier frequency shift. And what does that do? No effect on the image. So no effect on amplitude image. Because, same shift. Same shift for all frequencies. That's what the Fourier frequency shift theorem is. So, because same freak shift, all freaks. It's kind of like an echo centering error, basically. So, this was supposed to be frequency 4, but it was, we actually got 5, and then we put on 5, we'd actually get 6 because it squished it this way. So this was, this is, ky equals 4, but over here, it's, ky equals 5. So amazingly, it doesn't do anything. So all you'd see a phase shift in the image, but it wouldn't spatially, the important point here is it wouldn't spatially shift the image. And we know that these B0 defects cause a spatial shift, in a spatial distortion in the image. So I actually discovered this when I was preparing my homework, and I said, oh, this should, I did the Fourier transform. I shifted I put this phase error in there, and I did the reconstruction. I said, nothing happened. Why not? So that's not the reason. So what is the actual reason for this spatial shift caused by a local B0 defect in something like an echoplanar image? So how does the echoplanar data collection work? So we start in the center of K-space. We do an RF pulse that puts this into the center of K-space. And then we go down to the corner of K-space, and then we start recording data across K-space back and forth like that. And what is the end result? Well, the end result is that we're recording data over a long time. And so what's going to happen is we're going to have some phase shift that's bigger up here at the top of K-space than it is at the bottom of K-space. So, and why is that? Well, because it takes a long time to record this data, and so during that whole time, this little defect is doing its work, and it's slowly advancing the phase more and more and more for that particular point in space. And so when we get up to the top of K-space, the effect will have had the longest time to advance the phases. So there's our little defect. So the phase error is going to be worse here. So phase error worst here. So what will that do? So the way to think about this is, if we go back to that lecture where we talked about what if we sample K-space to different amounts. So we said if we sample K-space like 1, 2, 3, 4 this way in Y and this way in X, 5, and then we inverse Fourier transform that, say we get like square voxels of that size. Okay, so that's our ft minus 1. So that's our starting condition. But what have we done here? So what we've done here is we've got this phase advance, which is sort of increasing the spatial frequency by sort of making the stripes closer to each other. And so what are we actually doing? Well, we're effectively stretching K-space because we're getting up to a higher spatial frequency. So by the time we get up to the top of K-space, because of this defect, for that local part of the brain, the spatial frequency will be higher than it should be. We were trying to get up to, say, 128, and we'll get up to 130 or 140 or something like that. And so in our original discussion, if we sampled the same rate here, but spread out our samples here, what happens? When we do our inverse Fourier transform, if we go out to a higher spatial frequency, it's going to have our field of view and make smaller pixels. So what happens is we end up with the same pixels this way, but the pixels get smaller this way. They get half as big that way if we doubled our spatial frequency. So what's actually happening? It's squashing the pixels because we're actually sampling out to a higher spatial frequency. We were mistakenly sampling to a higher spatial frequency because this effect has been allowed to play out over time. Now, the important point here is that what's fundamentally causing this is the fact that we're playing out this phase error over time. So if we just had a plain old phase error that was the same for all time, then it would cause a spatial shift, because that would be the Fourier phase shift theorem. So if we just added some phase incorrectly to all of k-space, that would cause the image to shift. But what we're doing here is different. What we're doing is we're adding a phase error, but it's building up over time with the effect that we're effectively stretching the k-space and recording to higher spatial frequencies. And the effect of that is to shrink the voxels. And so what it's going to do, if here was your brain the way it was supposed to be, and you were supposed to have these voxels like that were nice and straight, what's going to happen is it's going to squash the voxels just in the part of the brain where we accidentally recorded spatial frequencies that were too high. And so what it's going to do is it will sort of like squash them like that and make them smaller. And then these guys will be all okay. So basically that's what's causing the shift. So the shift is coming from this increase in the spatial frequency that was caused by this extra B0. But it also requires that the effect is being played out over time. Because if the effect wasn't played over time, what you would do is you just shift the whole image. You wouldn't squash it. And so my original understanding was incorrect, because I said, well, here's the stripes we're trying to put on. We've got something that's messing up the stripes. It's squashing the stripes, but it's squashing all the stripes. And so when it squashes all the stripes, it's a Fourier frequency shift problem. All it does is mess up the image phase. It doesn't cause a spatial shift. So, what is the spatial shift caused from? Well, it's caused from three things coming together. So you have a static B0 defect. And then we have successive increases in phase error across k-space. And what that does is essentially higher spatial frequencies in defect area, and then that leads to smaller voxels. Squish. Now, it doesn't have to be squish. It depends, on the sign of the error. So if the error if the error was negative like that, it would do the opposite. It would sort of like lower the spatial frequency. And if you lowered the spatial frequency, then what would you do? You would stretch. So instead of you'd actually stretch the voxels out like that. And so depending on whether it's a positive or a negative defect, it's going to squish or, so here's squish, but we could also stretch. And then we could also reverse it if we went the opposite way through k-space. So you could do the opposite. You could start at the center of k-space, go up to the top, and then go this way. You can make the scanner do this instead. In which case the error would build up. The error would be worse down here. And so if you did that, then it would turn a stretch into a squish. So if something got squished and you really want to record it, you would probably want to reverse the order that you went through k-space and stretch it out instead of like squashing it all down into a little unrecoverable mass of pixels on top of each other. So that's the obscure reason that you get a B0 defect. It's not really from the Fourier phase shift theorem, because if you sort of mess with all the frequencies in the same way, that's actually an example of the Fourier frequency shift theorem. And what it is instead, it's a combination of these things. So you have like a static B0 defect. You've got successive increases in phase error, which means you're going up to higher spatial frequencies, which squishes your voxels. So that's the actual sort of reason for it. Now, you might wonder, why does it only occur just in the phase-encode direction? And that has to do with the fact that when you're going across k-space this way, this is a huge gradient. That's a huge gradient. And so the phase errors caused by these local defects are relatively small compared to that huge gradient. But this thing is this is a blip, is a tiny gradient. And so the phase errors are larger relative to those tiny blips. And so the end result is that you only see this effect in the phase-encode direction. And it's not because it's the phase-encode direction, because the frequency encode direction is also a phase-encode direction. It's just because the gradients are bigger. So the gradients are bigger in the frequency encode direction, and so you just don't see that. It's still occurring. It's just like a small fraction of a voxel, so you can't really see it. Whereas these little small blips, the B0 defect is bigger relative to them, and so you see all this effect happening in the phase encode direction, but it's not because it's phase encode, it's just because the blips are small. So this is kind of obscure, but it's something you deal with every day. Whenever you do an image, you're going to get a distortion, spatial distortions in the phase encode direction only, pretty much, that are mainly due to these buildup of error across k-space, resulting in essentially messing with the maximum spatial frequency that you went up to, also known as messing with your voxel size. And so that's actually what's causing this defect. And there's, just for the last -1 minute, there is another kind of defect that can occur that sort of looks a little bit like this, but it should be distinguished, and that's what we would call a dropout. So that's not the same, it's not quite the same thing. So what happens with a dropout? So one thing that can happen is if we're turn on a gradient with the goal to select a horizontal slice. So we turn on the gradient, And then we're hoping to select a horizontal slice like that. And how do we select that slice? So this is, gradient, plus narrow band of RF. So if we put a narrow band of RF, that should just select the guys that were resonating at this particular point in the gradient. So that's our standard slice select. But what's going to happen like over here? Well, there's a B0 defect. And if there's a B0 defect, what that's going to do is move the resonant frequency at that point so far off that we won't stimulate with this particular narrow band of frequencies. So the idea is we have this narrow band of frequencies, and that narrow band of frequencies is just supposed to hit the part of the gradient. It's just supposed to hit this part of the this part of the gradient, which will be the same across the whole head. And so if we've got enough of a B0 defect that it shifts the resonant frequency enough so that the narrow band of RF doesn't hit it, well, then we're hosed. And so that's a different thing. That's an actual dropout. So we didn't even. So what does the dropout means? It means dropout didn't excite spins in defect region. And so that can actually just cause like a little black hole in the image. It's generally in the same place as the distortions are. So you can see like there's going to be like some squishing, and then there might be like a black hole in there too. So there's just certain parts of the brain that are, so you might get like an actual sort of like empty black, that's supposed to be an empty black hole. So you could get both things, but it's a different phenomenon than the stretching business. And so obviously you can't fix the dropout by sort of unstretching it because the signal's just gone. Okay, so that was kind of a long lecture. Any questions about Fourier phase shift theorem, Fourier frequency shift theorem, or local B0 defect, which is this sort of combination of, a defect plus successive increases in the phase error over time across, k-space, over time. That's the critical part. And those two things together, end up causing this squishing. Okay, any questions? No? Okay, sort of okay. It's it takes a couple of years to actually remember it all, but there's always a first time.